The next presenter will be Gwyn Griffiths G3ZIL. He will be talking to us about contrasting effects of the 3rd to 5th November 2024 geomagnetic storm on reception in Colorado of WSPR transmissions from northeastern North America with those from Australia.
The 3rd to 5th November 2021 geomagnetic storm was a well-documented natural disturbance to the ionosphere. It coincided with some unusual observations of whisper spot reception by co-author Glenn Elmore in Colorado. And our presentation will try and answer the question, was there a causal space-weather connection? Glenn has a remote whisper receiving site at 7,500 feet in the foothills of the Rockies. It has the benefit of low local noise. Our study concentrates on the 7 megahertz band, where the antenna is a loop on the ground. Whisper spots and noise levels are recorded using Rob Robinette's Whisper Daemon software. To investigate whether the spot count collapse and the increased median distance were connected to the geomagnetic storm, we look at the whisper data, the contemporaneous online narrative, and space weather, including XSD region absorption and indicators from ground and space of geomagnetic field disturbances.
Excuse me.
These heat maps, noise.
Can you put your, switch your screen? We're seeing all of your notes.
Oh gosh, oh, right.
Just hit swap displays right there.
Okay, let's,
I think we have enough time if you want to start it from the beginning, so it's nice and continuous.
okay, is that the right screen?
Let's see. No, but just don't reshare. Just see where it says swap displays.
I'm sorry?
See where it says swap displays? It says swap displays right above your mouse.
Oh, right.
Yep, press that.
Yep.
Why don't you start from the beginning, okay?
Okay, so you're seeing the correct screen now.
Yes, it looks great. Thank you.
Okay. Right, let me turn the camera off then. Right. The 3rd to 5th November 2021 geomagnetic storm was a well-documented natural disturbance to the ionosphere. It coincided with some unusual observations of whisper spot reception by co-author Glenn Elmore in Colorado. Our presentation will try and answer the question, was there a causal space-weather connection? Glenn has a remote whisper receiving site at 7,500 feet in the foothills of the Rockies. It has the benefit of low local noise. Our study concentrates on the 7 megahertz band, where the antenna is a loop on the ground. Whisper spots and noise levels are reported using Rob Robinette's Whisper Daemon software. To investigate whether the spot count collapse and the increased median distance were connected to the geomagnetic storm, we look at the whisper data, the contemporaneous online narrative, and space weather, including XSD region absorption, and indicators from ground and space of geomagnetic field disturbances. These heat maps of noise level, number of spots, and median distance show what we mean by the anomalies. Each column is 1 day, and each bin in the vertical spans 30 minutes from UTC at the top. You'll hardly need me to point out the spot count collapse on the 4th of November. It decreased from over 230 minutes to under 20. The increase in median distance is from about 2,500 kilometers to over 12,000. The spot count and median distance anomalies persisted from about 0900 to 1300 UTC. More subtle and longer lasting is the slight reduction in noise level. Glenn's remote site is limited by propagated in noise. It looks like propagation changed to reduce the incoming noise coincident with the spot count collapse. Here's a summary of how the online sites Space Weather and Space Weather Live reported the storm. The precursors were M-class solar flares on the 1st and 2nd November. And the speed of the particles was such that the later, faster ones caught up the earlier, slower ones, and hence the description of a cannibal coronal mass ejection. The total result was a G3 class geomagnetic storm spanning the 3rd and the 4th. By the 5th, the storm was over, and reports of aurora had come in from California, New Mexico, and of particular interest to us, Colorado. Let's look at some indicators of the space weather. Images of the D region excess absorption are readily available on the NOAA website. We've compiled images 1 minute apart into these animations. Here's what was happening in the D region during the time of the whisper spot anomalies on the morning of the 4th. There was a modest absorption event primarily affecting Africa and the Southern Hemisphere centered at 1100 UTC, but there was no effect over North America. In fact, the major D region absorption event happened on the day before, at 1900 UTC, as the CME hit the Earth's magnetic field. But at that time, there was no standout event at Glenn's receiver. With excess D region absorption ruled out, let's have a look at other indicators of geomagnetic disturbance. Top, we have the KP index, here the planetary value, which was above storm level from midnight on the 3rd to midday on the 4th. Center, we have the magnetic field components from Boulder, Colorado, with the horizontal component in blue and the vertical component in red. The dip in the vertical component reaches a maximum just after 0900 UTC, returning to normal by about 1500. So this looks like a promising space weather connection for our whisper anomaly. And the Auroral electrojet index gives a circumarctic measure of the event from these 12 stations. Some of the orbiting satellites of the US Defense Meteorological Satellite Program carry spectrometers covering the short wavelength ultraviolet region where glow from aurora can be quantified. These images are readily available via a selector at this Johns Hopkins website. Satellite passes are every 101 minutes, from north to south and from east to west. Here I've created a composite of 3 such images for the morning of the 4th of November. They are disjointed as the aurora changed faster than the 101-minute orbit period. What's readily visible is that there was auroral glow between grid FN, Eastern North America, and Colorado. And furthermore, that the sector of paths to Australia was mostly unaffected, which is what was needed to result in a 12,000 kilometer median distance. The space weather connection is perhaps starting to come together. While the heat maps are great for quickly spotting anomalies, I do like time series graphs for detail, and I can control the font size. So here we have whisper spot count in 20-minute intervals from grid FN, Eastern North America to Colorado. The x-axis is the time of day, UTC. The dots with fine lines are the undisturbed days, showing both day-to-day variation and an underlying pattern with a smooth, sloped, sine-like dip centered on local noon. The thicker purple line is for the 4th. By 0900, the spot count had dropped well below normal, and then very few spots received until noon, while by 1400, the pattern was similar to that of a normal day, although later with more spots. But recall that we saw that the noise level was lower during and after the event. The pattern for the following day is also disturbed until noon UTC. Well, we've seen now this notable event at Glenn's Colorado site. How widespread was it? We've created this animation of whisper transmitter locations in green, receivers in magenta and red, and propagation path midpoints in cyan and blue. Although, like Chris's talk, this is a simplification. Each frame has spots in 10-minute intervals, and the time is up here in this box upper right. As a baseline, receivers that hear spots at the indicated time on the 1st of November are in magenta, and their midpoints are in cyan. While there is day-to-day variation, here at 05:15 on the 4th, there is a broad similarity between the path midpoints for the 1st of November in cyan and the 4th of November in blue. Let's run the animation. By 0800, we see that the 2 days are very different. We've lost paths, especially those with more northern midpoints. Now, by 1100, there were very few. There were only 2 spots remaining across the continent. So this was clearly not an event just at Colorado. This was a continent scale event. Recovery was initially patchy, with the northern paths recovering later than the southern paths. What would be needed to cause such a widespread collapse in WSPR spot count over North America? 3 possibilities are a much reduced signal to noise ratio, a much increased Doppler spread, or a combination. Let's try and quantify those factors. Looking at signals at N6GN from one of the stations with highest SNR, KC2TER in New Jersey, in this time series from 2000 on the 3rd to 2000 on the 4th, the cliff edge is clear. There is no spot with an intermediate signal level during this disturbance between -119 dBm and the limit of detection down at about -142. We'd need the signal level to drop by over 20 dB. Here on the right, we're grateful to Steve Franke for providing us this graph of WSPR decode probability against SNR for a range of Doppler shifts. Recall that WSPR tones are just 1.46 Hertz apart. There is a gradual, graceful degradation of probability of decode out to 2 Hertz Doppler. But by 3 Hertz Doppler, the probability of decode is less than 50%, whatever the SNR. Now, can we see evidence for either of both of these causes in our data? Here we've gone back to heat maps of the number of spots in SNR bins of 2 dB on the y-axis, SNR on the y-axis, and 10-minute intervals on the x-axis for the same set of Western North America receivers as in the earlier animation. If Doppler spread over 2 Hertz dominated, we'd expect to see a transition to few points with low SNR, with higher SNR spots dominating. While for the 4th, you might argue that there is some indication of loss of low SNR spots as we approach the cliff edge. It happens so quickly, we don't see much of a signature. If loss of SNR dominated, we'd expect to see a transition to lower SNR, which we don't really see. But what is still left is this cliff edge, this vertical cliff edge in the loss of spots. So it really is quite hard to draw a robust conclusion. And incidentally, it took 3 days for the number of spots to return to normal during that time interval after the event. Perhaps we can gain a better insight from ionosonde records. Unfortunately, we only have data at either end of our path. I've chosen to show Boulder at the west. What we see in a rather typical graph at 0700 is a maximum usable frequency of 6.7 megahertz at 1500 kilometers, followed by a drop to an MUF of 4.8 megahertz at 1500 kilometers at 0930. But note that the electron count in the black trace in these records has also dropped. By 1000, the echoes are faint, and there is no estimate from the automatic scaler for the maximum usable frequency, and no black trace for the electron count. but I'd welcome insights from those of you with more experience interpreting ionograms as to what these indicate and the likely effect on 7 megahertz propagation. Some ionosondes, but unfortunately not Boulder, provide information on Doppler shift from movement of the ionosphere plasma. These records are from the Idaho National Laboratory. So imagine you were looking straight up so that the center of these images is overhead and the edges are at an angle of depression of about 40 degrees. That's out at a range of 3 to 500 kilometers. And these ionograms are taken at 2 to 3 megahertz. There's significant variability between such images 15 minutes apart. So there is a real risk of selection bias, but here goes. The images at 0353 and 1338 show minimal Doppler, ranging to plus and minus a half a hertz, that's either side of 0. During the event at 0908, the Doppler is one-sided at plus 0.5 to plus 1.6 hertz. That is a movement of plasma toward the ionosonde. 15 minutes later, the echoes are now from the southwest, and the Doppler is negative 0.6 to negative 1.6 hertz. That is moving away from the ionosonde. But in fact, because of the being on each side, the movement of direction is the same at both times, from north to south. And while a Doppler shift of 1.6 hertz at 3 megahertz is equivalent to 3.7 hertz at 7 megahertz, there's more than sufficient Doppler in these records to greatly reduce whisper decode probability. So this is useful circumstantial evidence. Can we say anything about Doppler shift directly from whisper data? Perhaps. In some circumstances. Whisper spot data in the whispernet.org database is inadequate. The frequencies have been truncated to 1 hertz resolution. But Rob Robinet's Whisper Daemon logs 1/10 of a hertz resolution data provided by the standard whisper decoder as the average frequency. Glenn has a GPS disciplined oscillator for his SQESDR, as have some transmitters. So here we've taken 2 grid FN stations, AC2ZR in yellow and N8VIM in purple. And the time trace runs from 28th of October to November the 6th. The upper panel is the variance of each averaged received frequency over a 1-hour interval. The lower panel is the frequency anomaly, the difference between a spot frequency and the average frequency of the previous 30 spots. Now visually, the 4th of November is different on both metrics. If we had stationary statistics, the distribution of the variance should follow a chi-squared distribution, which is a special case of a gamma distribution. And here what I've done is to fit a gamma distribution to the AC2ZR frequency variance. The probability that the variance of just over 0.5 hertz squared at 0600 was from that gamma distribution was only about 1.5 times 10 to the minus 5%. It was clearly from a different distribution of greater than normal Doppler spread. And the lower panel shows we had anomalies of mean frequencies over 2 hertz before and after the gap. Finally, let's get to why the median distance leapt to over 12,000 kilometers. The paths from Australia to Colorado likely had their last encounter with the ionosphere well to the south of where we saw auroral glow in the satellite images. In the upper graph, the black line and dots are the spot counts in 30-minute intervals averaged over 28th October to November the 2nd. On the 3rd in blue, the pattern was quite different. And that uplift in spot numbers persisted to the 4th, right during the time of the spot count collapse for North America. While the noise at Glenn's site had dropped by 2 dB on the 4th, this was not the case of the much higher number of spots. Looking at histograms of the SNR between the 28th and the 2nd, and then the 4th, There are many more spots with SNR over -16 dB on the 4th. It's not simply +2 dB due to the lower noise. I've no explanation for this uplift. Perhaps a speculation it might be due to the higher X-ray flux from the earlier CMEs. And so in summary, we've shown how a sudden precipitous drop in WSPR spot counts across North America was associated with a G3 magnetic storm. The timing and duration coincided with the dip in the vertical magnetic field component at Boulder and with auroral glow observed by a satellite. Ionosonde records showed reduction in electron count in MUF and increased Doppler. Both would lower the probability of decoding WSPR spots. In contrast, the last ionospheric refractions for the signals from Australia were to the south of the Auroral disturbance. Glenn and I now have buried magnetometers and we're automatically capturing WSPR audio files, hopefully for the next event. Thank you for your attention.
I'd like to thank you. Thank you very much. Thank you, Gwyn. We'll take 1 or 2 questions. No? I think everybody's, we have 1 question from Bill Engelke.
Do you think that the change in spot count that you observed during this event could be observable in the Tonga explosion, possibly?
I've not looked at that, Bill, but using the methodology, we'd certainly be able to try and look at it.
Thank you so much, Gwyn. We really appreciate it. So nice of you to join us from across the pond there. And Chris, Deacon as well, and all of our other speakers.